so let us add a couple of layers to our linear model, make a multi-layer neural network or a multi-layer perceptron. We are going to practice a few coding hygiene while doing that, such as device placement, patch shapes, and the use of right loss function. We'll keep it simple. So that means that we'll move some of the monitoring and visualization parts of the code to a companion notebook. Okay, so let's import a few modules. We are already familiar with this. We are going to use a data set here, fashion MNIST. And if you go to chapter 4.2 in the book, there is an explanation on this benchmark data sets that we can try our machine learning algorithms and compare them. One of the most famous one is the MNIST data set. And as you can see here, even simple models are now achieving a very good accuracy. So to make it more challenging for ourselves, we are going to use the fashion MNIST data set. And this data set is in the Torch Vision library of PyTorch. So we are going to use that and to try our methods on it. With that, we need to import the Torch Vision and some tools within it, including dataset. So notice that I included transforms to use the image transformations tools within Torch Vision, such as conversion to tensor, normalizing the images, and so on. Here we want to work with or specify the device. And the reason is, first we will make a small tiny MLP, but then later we will add more layers. So we may need to use CUDA or GPU. So for now, we will continue with CPU, but in any case, if we want to use the code later, we have to determine the device, and when we change it, we don't want to change the code accordingly. Okay, so now let us download the fashion MNIST data. Downloading the data to a data folder in my root. And here, notice that there is a transformation that basically converts the NumPy or PIL image data to Torch tensor. It also scales the pixel values from 0 to 255 to 0 to 1. Reorders the channel widths and heights, transforms it to a standard format of channel as the first dimension, and then height and widths. In the case of fashion MNIST image, it will become, as it's a one channel grayscale, so it will be one channel and a 28 by 28 square image. Okay, so let's download the data. So if you go to the root directory, you see that the data is now available. So the train validation split will leave about 10,000 images for our validation set, and the rest, which will be 50,000, would remain for our training set. Okay, so we are going to use random split, and we are going to use this as a generator, basically only load data when we need. Okay, and let's simplify. This is the train and validation data set. And if you remember, the random split comes from the utils.data. Okay, so now we can make our train loader and validation loader. So the train loader is basically a data loader. I mean, let's look at this, that it gets the batches. Here we shuffle it during the training. I want to reduce the size of the train loader to basically better utilize GPU, because we are going to do a lot of batch, use a lot of batch during the training. We don't need to be that savvy or stingy on the validation, because that's not really the bottleneck. So I'm going to actually increase it to emphasize. With that, we can actually check the code. So let's see. We can get a X and Y batch from our train loader, and then we can, of course, print the shape. I also want to plot one of these images. So let's do it. So let's first run this, and then I want to visualize the first image of this batch in the X batch. Okay, so to do that, I'm going to use imshow, and here it takes the X batch 0, and here remember this is the second. So first dimension is the number of batch, and here the first batch we get 64 images, and the second one is just a channel dimension, which here is a one-dimensional channel, if you recall. And here one trick is to, instead of doing this, just say that squeeze, meaning that give me a view of the tensor where we remove the dimensions of size 1. So this way we basically remove the unnecessary dimension that don't carry meaningful information. And remember, this is a view, so we can do the reverse of this squeeze and go back to the original view. Okay, so let's plot this, and this is an image of a shirt. Okay, so everything looks good, and we can go on and make the model. Okay, so now we want to make the layers, so we can get the can introduce self dot layers, or let's just be more expressive here, and sequential. It flattens the input. It adds a first layer going from the input to that, and let's accept this. So one layer, one ReLU, and then last layer. I want to add another layer, so let's add another layer, and here an linear. So let's reduce this since I'm adding another layer. So 128 to 64, and another ReLU, and then the final output here. So notice that the output is the output of the linear regression, meaning that they will be real valued, positive or negative, not necessarily bounded to 0 and 1. So this is actually a logit value. It's not a softmax value. So remember that, because that will be important in our later stage. Okay, so now that we have the architecture, we can write the forward method, and we are done with the class. And here I want to add a function that computes the accuracy of the network, and we can write it as accuracy. So takes the output of the forward method, which, like I said, there are logits and the labels or the Y values. And it takes the maximum logit value that corresponds to the prediction of the classification. Because if you remember, even if you do the softmax on the logit, the maximum value is the same. And it checks if that maximum value is the same as the label. And that's basically the number of true positives. And then len of pred is the number of all predictions. So this is the accuracy. And remember that this should not use the gradient. In other words, we want to disable the gradient tracking inside this function, and there's a easy decorator that we can use. So torch no grad. So this way, this function will not track gradients. It saves memory, of course, and speeds the evaluation. Okay, so let's write a function that trains one epoch. Okay, so then the total loss, and we want to track the total loss, total number of correct, and total itself, which start with zeros, and then for X and Y in the data loader. So notice that the suggestion already did sending the tensors to the device, and this is important, like I said, when later we change the device, so this will be done automatically. Here I want to zero the optimizer first, so this is optimizer, and then we get the output. So let's just call it logit for the sake of clearance. So here the output of this model will have this shape, basically the number of samples in the batch and for the batch size, and has and a logit value. So we will have some criteria here, and the criteria is we get this from the argument. Remember that we write the function in a way that if we change the loss, it doesn't really change itself. So the loss can be fed from outside. Okay, it takes the logits and Y, and then backward optimizer step. Okay, so let's review the suggested code. I see that the code is independent of the batch size, meaning that it doesn't count the number of correct prediction within a batch that may have different size, right? I mean, when we are sampling from the loader, it's possible that we accidentally get different batch sizes, and or even in the validation set, if you remember, we chose a different batch size. So let's make the code be sensitive to the batch size. So with that, gonna make a batch size variable that gets that, and then we have to update the code accordingly. Okay, so let's see what we have. Total loss item. So this is a total loss that should consider the batch size. I want to make this line be independent of the function accuracy. So let's just write it by hand. And then here we are returning also the fraction of correct. Okay, so with the same logic, I'm going to write the evaluate function. Then we can train our network. Okay, so the model is the simple MLP. We send it to device. Of course, you have to always remember that the model goes to device. The criterion is the cross entropy. Here we are using Adam. The learning rate is that. And let's use what we learned, the L2 regularity. And here the L2 regularity is implemented using this option, weight decay. And if you think about this, when you are doing the training, during the training, the weight sometimes increase and basically using more variable. And when you increase the weight, the gradient steps are getting smaller with respect to the weight sizes, the norm of the weight. And the weight decay makes sure that the gradient steps remain efficient. We can talk about that during the class time with some maybe geometrical interpretation. Okay, so weight decay introduces the L2 regularization. Let's train the model for a small number of epochs. I want to keep a record of the history, so let's do that. Then let's populate the values in the history dictionary. We can also print it out. Okay, so now we can run the code and wait for it. In the meantime, maybe we can write a function that can visualize the loss history. And also the train accuracy. See that both training loss and validation losses are going down. Their accuracies are going up, and that's of course a good sign. And since we are waiting for this, just a review. So what we were careful about during the code was the batch dimension preservation. We want to make sure all operations maintain the batch as the first dimension. We want to make sure all of these operations are processing the entire batch simultaneously. So that's the vectorization and the shape transformations that we did over the images from the data set. Of course, device consistency were also important. We want to move all of the tensors to the same device, either GPU or CPU. And then at the end, the handling of the cross entropy loss that averages over the entire batch by default. Okay, so the trainings finished, and we can plot that, and you see that the loss is going down consistently and accuracy goes up, and which shows that it's worth it if we increase the epochs, and maybe even if we are not happy, if it is plateaus at some point about 90%, of course that means that our network is small and we can increase the number of layers. So let's do that. Why not? We can make a deeper MLP. Let's just call it plain MLP for now as a base class that we want to maybe go fancy with it and add some residual blocks if we go deep on this. Okay, so that, and let's initiate it and add the layers. I want to add the arguments of some of the architectural decision here. So input dimension is fixed. which is a 28 by 28, but we want to have a control over the hidden dimension and the depth of the network. And of course, the output dimension is 10, so we can do all of it from here. Okay, so let's make a list that shows the layers, the architecture and the activation in each layer, and then we can append to this list, and then later we will basically go over the list and add them one by one in the sequential NN module. Okay, so layers. We start with the first one, which is a linear layer. Okay, so I see the suggestion is what I want, and we go over the depth and y minus 2 minus 1. So note that I fixed the hidden dimension for all of the layers. This basically simplifies the shape management that we are doing here. Okay, so we have all of these layers, and let's just knit them together. Okay, so I see. That's why we have the output layer separate. So actually don't like the fact that self out is different. So why not doing this? We just add that, right? So we have to update the forward. So here you notice that my input is a 28 by 28, and I like to make sure the image is flattened. To do that, if x dim is, for example, more than 2, we just basically get a view that is flattened. So now that we have a fairly deep MLP, let's compare it to an equivalent size MLP that has a residual connection. Okay, so with that, I'm gonna first write a residual block that I will use it just like any other blocks that sequentially will be linearly connected. So first, let's write this block, which is an NN module. And for residual block, if you remember, we have to say the dimension of the input will stay the same. And here, before jumping, I want to write a reminder that in a residual block, we have a residual mapping that has the same shape of x and basically give us a x plus fx. Okay, so here we want to write the fx. So for that, self of f is a NN sequential, basically a linear, a ReLU, and a linear. And then we add the x following that. So because I'm going to knit these blocks together, I want to add a ReLU here. So torch ReLU, and then this. So this way, I don't need to write the ReLU again and again. And this is called a post activation design. And now we can use this in our residual deep network. So we have a residual MLP. We try to keep everything similar to what we had. Notice that I have a hidden dimension, meaning that I have to first project the inputs to this hidden dimension and then do the residual on that. So I need an input layer, and that basically takes in the input dimension, map it to the hidden dimension. Okay, just like before, we have the self-net. Okay, so notice that I don't have a ReLU between the input and the rest of the layers. So let's rewrite this. Maybe we can, instead of doing this, we add the ReLU, and then now we have this list that we need to, of course, zip, and then we can finish off with an NN layer linear x to the output. So what to fix here? We don't need this anymore. Yeah, let's keep this for now. Okay. And we just add this in the forward. Okay, we are going to use the previous functions and evaluate and train epoch, and then build the plain deep MLP and the residual MLP. Let's increase the depth and send it to device. So this is the plain, and the residual is deep residual MLP, and we keep the dimensions the same. So similar capacity. We are comparing apples to apples, and the criterion is still cross entropy. And let's just set up the optimizers for each one of the models, which is again same, still apples to apples. And then we can do the training loop. Let's do it for $80. We did it for 10 next time, but this one is more expensive, so I'm gonna do it for 10. Okay, so we have the code. We added the device and looks like it is running. Okay, so the results is here. And as you can see, the residual net is working pretty good, better than the shallow MLP. But you see that the plain deep MLP is not really working. And the main reason, as we discussed, is the depth and the way that the gradient is vanishing. There are ways to investigate this. For example, maybe we can reduce the weight decay. We can work on the normalization, batch normalization, and things like that, and make the deep MLP better dealing with those things. But the main point is when depth increases, it will be more challenging to keep the gradient flow backward and richness of data forward.